All right. Good evening, Charmaine.
Evening.
All right. How are you doing?
About
Can you repeat? I'm not hearing you.
that's about different. I'm having sinus issues. That's about.
For some reason, I'm not hearing you. Let me try my volume. It's maxed.
You hearing me now?
Yes, I'm hearing you now. How are you doing?
That's a good sign of
Oh, sinus?
Yeah.
Okay. All right. So we're at the last topic, which is hypothesis testing. And once we do this, we can then look at last year paper. And I just want to apologize for, sending it this late, but during the weeks are really hectic. Like when I tell you it's hectic, I have
I understand.
yeah. So
students, yeah.
yeah. So because it's so hectic sometimes, just don't get the time. But finally got the time right before. So yeah, this is a past paper from last year. Once we finish, we'll go through everything. All right. And if I sound a little tired, it's because today I had a marathon session. So for CSEC. So, yeah. But, we're still up and ready to have some fun because statistics is the best thing ever, right? So we're about to have some fun. So what we're getting into now, this is the notes for
I didn't send the last week notes today. I didn't send those.
I didn't send last week notes.
No, you only send the recording.
Oh, I didn't send the notes for I didn't send the notes for confidence interval and proportions.
No.
All right. So let me just do it now because just do it now. Give me a minute so I can send it. How was the second mid-semester?
It was out?
Repeat?
What do you mean? Grades are not out?
No, how was the second mid-semester? You should have got back a grade.
When? I didn't know that grade was out.
Yeah, grades are out. I got back from the 6 persons I tutor, I got back from 4 persons.
Oh, check.
Yeah.
Well, maybe it wasn't that bad because I don't really chat in the group. But I don't really look at the group anymore, so I don't know.
Oh, you haven't looked at it?
No, I said I don't really talk in the groups. I don't know what is going on. I just ignore the messages that come in.
Okay, I understand. Yeah. All right, but you can check and let me know. So, yeah. Let me find the notes. Sampling distribution and confidence interval. All right, I found the notes. So here it is. All right, I just sent them.
Okay, no problem. Thanks much.
All right, so now we're going to be looking at hypothesis testing. Now, hypothesis testing, these are the 5 main things that you need to know. Null hypothesis, alternate hypothesis, test statistic, rejection region, and then what can you conclude? Those are the 5 things that you need to know at the hypothesis testing. Now, how does this hypothesis testing come about? Maybe let's say, for example, Charmaine, both of us, go somewhere and we're observing an event. And we're observing an event and we say, maybe event A cannot do this another time. You propose that to me. And that's your hypothesis. You're saying that this just can't happen. And I did there and I say, no, it can happen. And so, of course, now we need to be able to do some sort of inference based on the data that we have to make a conclusion, to decipher, do we have enough evidence to predict if something is true, yes or no, right?
Right.
Yeah, so we need to be able to make a decision. So this is a part of inferential statistics now, known as hypothesis testing. So you always hear the statement, they say innocent until proven guilty, right?
Yeah, right.
So let's say, for example, you told me like track and field. So let's say, for example, you tell me that Elaine Thompson Francis, she's going to break the world record, right? That would be your alternate hypothesis. Whatever you propose, that'll be your alternate hypothesis.
Okay.
But the null hypothesis would be starting with, she's not going to break the record, right? So that would be the null hypothesis.
So the null would be, I am saying that she's not going to break it.
No, yeah, so the null will be she's not going to break the record, and the alternate is what you're trying to prove. The alternate is always what you're trying to prove. All right. So in the same way, you can maybe make a statement to say, let's say, for example, just another example thrown out there. Maybe I say to you, Charmaine, that I am going to be a big time statistical lecturer in the next 10 years. And maybe you say, no, Ronaldo, that is not true. You're not going to be a big time lecturer in the next 10 years. Then of course, that statement that you propose would be the alternate hypothesis. All right, whatever you're trying to prove is going to be your alternate, and then the null hypothesis now would be, of course, the negation of that. When I use the word negation, I just mean the opposite. All right?
Okay.
So after we talk about null and alternate, so here it is now. So the statement that the experimenter would like to prove, we call that alternate. Whatever you want to prove, we call that alternate. The null is the hypothesis we want to be able to detect if it is true. So alternate, what you want to prove. Null now is what we want to be able to detect if it is indeed true.
Okay.
Now your test statistic, test statistic is the value of Z. Anytime you have a normal distribution, really and truly, the only thing we can find is Z. Your test statistic is finding Z. And this will be able to help us to make a decision on whether we're able to reject or accept the null hypothesis. The next thing is what we call the critical region. The critical region is just those points that will allow us to make a decision to reject the null hypothesis. That's all is a critical region. Now, don't worry, you're going to just be able to look at a formula and swat it. And then if the test statistic is bigger than your critical region range of values, then that's the only time you'll reject the null hypothesis. But we'll get more into that soon. This is just looking at definition.
Okay.
All right. And then of course, we're talking about hypothesis. So we have to make a definition of what's hypothesis. So a hypothesis is just a logical guess about something, right? A logical guess. So therefore, a statistical hypothesis now is a statement about the parameters of one or more populations. And then from that, we're able to decipher if using our statistic, if we can make a conclusion about these parameters. So that is a statistical hypothesis. So no, we're no longer just using regular hypothesis where, we just wake up and we say, oh, I just feel that today it's going to rain. we're now looking at a statistical approach to it. We have to put some data to it. We can't just make blunt statements like that with no data to back up our arguments, right?
Okay.
We have to have some numeric figures. Now, don't worry about the types of error, right? Types of error is just talking about when we're going to reject the null hypothesis.
Okay.
So you have two types of error. You have a type 1 error. A type 1 error is a statistical test in the error made by rejecting the null hypothesis when it is false. That's type 2. Oh, because I skipped over type 1. Okay, here's type 1. So type 1 error, only thing this is saying pretty much is once you calculate your test statistic, if your test statistic is giving you a value that you're able to reject the null hypothesis, then it's a type 1 error. That's all it's saying. As I'm saying, you don't need to know these technical terms. These technical terms are for persons who are maybe going to do, you know, some sort of inferential statistics next year. The definitions are there for when you go deeper into statistics, which you don't necessarily need to know. So we won't waste time on that because we're gonna have to look at the paper as well. So, you know, you can read through that. These are just definitions, but again,
No problem.
you don't need to know it. Now, what you do need to know is rejection region and critical region. So rejection region, so let's talk about those. Now, rejection region, as we said, is whenever you compute your test statistic, there must be a region of values that will tell us if our statement is true or false, right? Now, the region where the values is going to be such that our statement cannot exist, in that case, now we call that the rejection region, since our test statistic doesn't satisfy that criteria. And that would be the rejection region. Of course, when we hear it in words, it just sounds like a whole heap. When we actually do some calculations, it gonna make a whole heap more sense. So don't make the words sound like it's difficult, it's really easy. Now, of course, there's always two types of alternate hypothesis. All right. So the first one is known as a one-tailed test alternate hypothesis, and the next one is known as a two-tailed test alternate hypothesis. Because maybe, for example, let's say, for example, maybe you have an uncle and he's just making a lot of money, right? And your uncle said, you know, I think I make about $800,000 per month. That's what he says, right? Your uncle say make about 800,000. Now, maybe you could propose that he make less than 800,000. Maybe you could propose he make more than 800,000. Or maybe you could propose and say, uncle, you don't make na 800,000. Notice three things there you can propose. You could either propose it's greater than the 800,000, less than the 800,000, or not equal to the 800,000. See that?
Okay.
Now, the first two cases where you'd propose, where you're saying is either greater than 800,000 or less than 800,000, is what we call a one-tailed test. That's a one-tailed test alternate hypothesis. So you're just looking if it's either greater than the mean or less than the mean. Now, a two-tailed now is when you propose and you say, uncle, you don't make 800,000. So by proposing this statement now, the two-tailed test, you're saying that uncle is either you make more than it or less than it, but it just can't be the 800,000. That's a two-tailed test because there's a greater chance that you can be correct with a two-tailed test, don't it?
Mm-hmm.
Yeah, because that's just a set amount. So of course there's a greater chance that you can be correct here. But that's a two-tailed test. All right. So now before we look at this example, there are some formulas that we're going to look at now in order to do hypothesis testing. So this page, I want you to write it down. This is all you need to know in hypothesis testing. This is what it boils down to. This is what it boils down to. Oh, I don't open up my alpha over 2. I don't open up my alternate. Where's the table with? I'm gonna have to open it in Google. I don't think I have it here. I want you to write that down in the meantime. Let me take this down. Can't find the table online here. I have a physical copy with me, but I don't have the table. When we're doing question, we have to have the table. Now, you don't have to worry about the table because they're going to give you the summary table to use. Trying to see if I have a PDF copy. I really don't. I have one right here beside me. All right, I'm gonna take a picture and scan it. You have to have this table. All right, I'm just gonna WhatsApp it to you, okay?
Okay.
I just shared it by WhatsApp. So there's a table and it's called table 5 and it says percentage points of normal distribution. So I want you to look at that, all right?
Okay.
Yeah, all right, but let's get back to it now. So right here now, as we're saying, the null hypothesis, we call the null hypothesis H naught, meaning the null hypothesis. The colon I mean just mean given or such that. So the null hypothesis is such that we're proposing that the mean is equal to whatever the mean is that we're proposing that it is in the question. The question will give you what this is. Now the alternate hypothesis is going to be either you're saying that it's actually bigger than that mean or it's less than that mean. That's where this formula would come in play. Or if you're using the two-tail test, the two-tail test now would be H1 is such that it's just not equal to the mean that it's in the null hypothesis.
Okay.
In the test statistic, we know to find test statistic already. It's the sample mean. So it's now just this, whatever we're proposing, whatever X value, X minus the mean now in the null hypothesis divided by the standard deviation. And we know the standard deviation, because we learned sampling distribution, we know it's sigma over the square root of n, right? You know this is the same formula for z from last week. Now, when you get that z value, that is your test statistic. This is how you're going to know when to reject now. So you reject the null hypothesis if this is true. If z is greater than z alpha, where alpha is your level of significance given, or z is less than minus z alpha, that's when you reject the null hypothesis. I don't like to see it this way. I like to write it the other way around. Z is less than minus z alpha, or z is greater than z alpha. That's for one-tail test. Now, for two-tail tests, what we need to show is that the magnitude or the modulus of z should be greater than z alpha over 2. Now, modulus just means absolute value. Absolute value just means if the number is negative, the absolute value of a negative number is the positive of that number. For example, the absolute value of negative 1.63 is 1.63. That's the absolute value. Modulus, this weird symbol around it, just means the absolute value of it. Okay? That is what we do for the two-tail test. We need to show that the absolute value of z will be greater than z alpha over 2, where alpha is just your level of significance. So as we said, if the value of the test statistics lies in the rejection region, that's the only time we reject our null hypothesis. Otherwise, we cannot reject our null hypothesis. So let's go ahead and look at an example doing this question here. So here's a question. It says, a machine fills packs. A machine fills packs. Let me just copy it. Go into the white screen. So it says a machine fills packs with liquid and packs are then frozen. Space is needed in the packs for liquid to expand. Hence, they cannot be overfilled. And then they said the volume of liquid in the packs follow a normal distribution with mean 50 and a standard deviation of 2.5 milliliters. So just writing it down, X or bar X in that case follows a normal distribution with mean 50 and a standard deviation of 2.5. So of course, we know that since it's sampling distribution, it's the variance, so it's 2.5 squared divided by n, and n in this case is 50. So this is the distribution it follows. Now it says the machine breaks down and is repaired. The next batch of production, it is suspected that the mean volume of liquid dispensed by the machine into the packs has increased. So this right here is our proposed or alternate hypothesis. So it is suspected that the mean volume of the dispensed liquid by the machine has increased. So what we're then saying is that our null hypothesis, we're proposing that the mean has not increased. So if the mean has not increased, we're proposing that the mean is equal to same 50. We're saying that the mean is still 50.
Right.
Now the alternate hypothesis is if we propose that it's increased, we're proposing that the mean is now greater than 50. See how that nice?
Oh, so this would have the null one would be equal to 50.
The null is always equal to.
Right.
But then you're just looking on whether it's going to be greater than, less than, or not equal to for your alternate. But in our case, what we're trying to prove that it's the alternate, that it's greater than 50, because so what to underline, it is suspected that the mean has increased. Increase mean that it's bigger than 50 now, right? So now it says, so now it says, the manager takes a random sample of 50 packs and find the mean volume of liquid in these 51, and there is 51 milliliters. So then find out, say, the mean volume for the 50 samples is 51. Does this provide enough evidence that the machine is over dispensing? So we don't know. So from the 50 samples, the mean is 51. That might be suggesting that it's increased, but let's test it out. No, they didn't give us a significance level. Anytime the question don't give you a significance level, you always take the significance level to be 5%, all right? Okay. Anytime they don't give you, take it to be 5%, because we want to be 95% confident. So taking that, it's a 5% significance level. So therefore we can be 95% confident in our answer. We always take it as a 5% significant level question. So first thing we need to do is find our test statistic. So our test statistic, Z, is now going to be equal to, remember, it is X, the X value that they give you, 51, the proposed mean from the random sample now, 51 minus the original mean of 50 divided by the standard deviation 2.5 divided by the square root of 50. So just put that into our calculator. So just put that into our calculator. Oh, good. So 51, let me just take out the calculator. So taking out the calculator, I know it disappeared the whiteboard. It seems I can't present the calculator and the whiteboard simultaneously. 51 minus 50 divided by 2.5 over the square root of 50.
2.82.
2.82, very good, that's correct. Or 2.83 actually. We round up. Yeah, 2.83. So that's our test statistic. So remember, because it's greater than 50, it's a one-tail test. This is a one-tail test. So since it's a one-tail test, remember the rejection region for one-tail test. The rejection region is if Z is greater than Z alpha. So Z alpha now, this is our, so let's find out our Z alpha. So our Z alpha is Z of 5%. 0.05. So let's find out what Z 0.05 is. So remember the picture I just sent you? I want you to look at P being 5 now. 5%, you're going to say 1.6449. You see that?
It is so done. P.
So you go down to table 5.
Right.
And you see percentages, the P mean percentages. So P, you look for 5%. 0.05 is 5%.
0.05.
So you're looking at 5%, 1.6449. Do you see it?
Okay. 1.6449.
Yes. No, right. I think I should have the P. Wait, let me just see something. I know I had it. Where is it? Where is it? Where is it? I know I have the one that's, let's see. It would have been given in one of the worksheets. I'm just looking for the worksheet.
Alpha is the same thing as bar X?
Can you repeat?
Is alpha the same thing as bar X?
Alpha no is just the significance level. They're gonna always give you the significance level though, whether it's 5%, 10%, 15%, they're gonna give you. I'm looking for the problem set. It should be in one of the problem sets. I'm just finding the problem set. All right, here it is. It should be inference for mean. It should be here.
So once it's greater than 50 is a one tail, right?
All right, so here it is. Well, they don't give you it properly here. This is for two-tail test though. So they only give it for, this is just a two-tail. I'm trying to find the one for one tail. This is two-tail tests.
Oh,
So they give you
the same table they use.
they're giving us the values for two-tail. So notice they round up 1.6449 to 1.645. But this is only two-tail. This is when you use for two-tail. I'm looking for the one for one tail. They don't have the one tail there. All right, but when I find it, I'll show you. But that's for two tail. So this right here now is for a one tail test. So Z is greater than Z alpha. Now remember, our ZO phone was 2.83. So my question to you is 2.83 greater than 1.6449?
Yes, it is.
Yes. Since it is, yes. We're right. There is enough evidence to reject the null hypothesis. So in a question like this, you tell them there is enough evidence to reject the null hypothesis at 5% significant level. In that case, the mean volume has increased. In that case, the mean volume has increased. That's it. Nice, don't it?
Mm-hmm.
No stress at all. That's that question. Pull it this.
Okay.
All right. So you don't need to write down this one for the first one because the first solution should be in the notes. It's just that the rest of them is not done. So here it is. This should have done it. Of course, the solution has a lot more chatting in it. Let X be the volume because you have to define your variable, but we're not preparing for a paper 2. Of course, if it was a paper 2, then we'd have to define our variable. You can't just start with X and we don't know what is X or bar X. So you let X be the volume dispensed by the whatever, the standard deviation 2.5. The alternate is that it's increasing. The sample mean given was 51, get the 2.58, significant level 5%, Z alpha 1.645. Since the test statistic is greater than the critical value, we would reject the null hypothesis. The only blemish from this here, right? So the only blemish from this here is, as I said, we would add and tell them, in that case, the mean volume has increased. So it has increased from 50 to 51. Or we don't know how much it has increased, but it has increased from 50. Cool?
Okay.
No, that's it for that question. Now, of course, we're gonna do a couple more together. So, you know, you feel nice with it. Look how many questions we have here. We have 1, 2, 3, 4 more can do. And after that, we have some proportions one can do. Nice, don't it?
Okay.
All right, but we'll just do two more regular ones, 2 proportions, so we can go to the paper last year. Because can you imagine? We finished now, it's only up to you now to revise, look at everything that we've done. We've covered everything. only up to you to now just revise. And as I say, when we go through this paper, you're going to realize it well easy, right? And the level of questions will be on the same level. It's just that it might be new questions.
Okay, but it's the same procedure.
But it's a similar procedure, yeah. Similar, same procedure, yeah. So copying this one, it says, experience has shown that the scores in a particular test are normally distributed with a mean score of 70 and a variance of 36. Now notice they give us variance. So in that case, they're telling us that the standard deviation is 6. No problem, variance is 36. It says when the test is taken by a random of 49 students, the mean score is 68.5. Is there sufficient evidence at a 3% level that these students have not performed as well as expected? Notice they're saying, is there evidence to suggest that the students didn't perform as well as? So we're saying, did the students perform worse than the expected average of 70?
We don't know that.
We don't know, so we're gonna have to test it. So first we're gonna say is X follows a normal distribution with mean given is 70, with variance divided by sample size. So the variance 36 divided by the sample size of 49.
Right.
In that case now, our null hypothesis is always that the mean stays roughly the same. So we're saying that the mean test score is 70. Now, what we are proposing is that did students perform worse than? Did students not perform as well? So well would be 70 the benchmark. So did students actually perform worse than the 70? That's what we're trying to find out, right?
Right.
Let's hope they didn't perform worse than 70. So that is our alternate hypothesis. So now, the test statistic Z now, remember Z is equal to the X value given, which is the sample mean given. The sample mean is 68.5. 68.5 minus 70 divided by the standard deviation, which is 6, divided by the square root of n. And the square root of 49, we know that is 7. So plug that in the calculator. Plug this in the calculator for me.
Negative 1.75.
Negative 1.7, how much?
5.
7.5, good. Now I want you to remember this. Going back to the notes, I just want to show you. Remember, there's 2 things for rejection region for one tail. But remember, when you're looking at a one tail, when it's less than, you're going to be using this as your rejection region. When you're looking at one tail where it's greater than, then you use this one as the rejection region. You have to make note of that, you know, okay?
So when it's negative, we use this one over here.
Repeat.
When it is negative, we use Z is less than
minus Z alpha, yes. So let's check that out now. So going back to this question, our rejection region now is that Z is going to be less than negative Z alpha, but alpha here is at 3% significant level, so that's 0.03. So I want you to go down and look at 3% and tell me the corresponding value for 3%.
$1.8808.
1 point how much?
8808.
Very good, yes. So now our Z, let me change the color. Our Z is negative 1.75. We're saying that's less than negative of 1.8808. Now, is that true? Is this less than negative 1.88?
Yes, it is.
No, that's not true. Negative 1.75 can't be less than negative 1.88.
This is
Negative.
this is 1.88.
Yeah. Imagine I ask you this, is negative 1 less than negative 2?
For them negative. It's like,
Is negative 1 less than negative 2?
no.
No, so negative 1.75 can't be less than negative 1.88. If we were to look at a number line, look at this. This is a number line 0, 1, 2. Here, negative 1, negative 2. Negative 1.7 maybe is here. Negative 1.8 is somewhere here. Negative 1.7 bigger than negative 1.8. So can't say negative 1.7 is less than negative 1.8, right?
Okay.
Agreed?
Yeah.
So in that case now, we can conclude that, of course, since this is not true, so we cannot reject the null hypothesis. There's not enough evidence because the rejection region is not satisfied. So rejection region not satisfied. So in that case, we do not have enough evidence to reject the null hypothesis. In that case, what we're saying is we don't know if the students perform worse yet or no. We just don't have enough data to gather that information. The mean score being 68.5, it doesn't give us sufficient evidence to say yes, right? So I like to think of this as guilty, innocent until proven guilty. So somebody come in and say, look at the mean score for the class, 68.5, 170. The class mean is poor. The class mean is dropping. Well, clearly, we could do some statistical inference and show them that, well, we don't have enough evidence, right? So this is what I like, statistical evidence. Yeah, man, statistical evidence. This is evidence that they need to start using in court now. They need to start having, they need some ways to just put in statistical data now. So everything is fine, don't it?
Yeah.
Yeah, so we can say, no man, he's not guilty or she's not guilty. We just need some statistical evidence because you cannot dispute the numbers. The numbers never lie. Men lie, women lie, we all lie, but numbers cannot lie. That's the beauty of the numbers itself, right? All right, now this question here now, it says, I want to look at one more. All right, yeah, let's look at this one. So it says a normal distribution is thought to have a mean of 50, blah, blah, blah. So we'll do that one. They will look at a proportion question. Hopefully this is a two-tailed now. So we'll get a two-tailed example. So far we've seen one tail and we want to see a two-tail. All right, so this question here, it says a normal distribution is thought to have a mean of 50. A random sample of 100 gave a mean of 52.6. And they say, and the standard deviation is 14.5. I'll just call it X. X have a normal distribution mean of 50. And the standard deviation is 14.5. So that means the variance would be 14.5 squared divided by the sample size. The sample size is 100. Now it says, is there evidence that the population mean has increased? Again, this is one tail test, right? because it says has increased.
52. What about this part? It's a random sample of 100.
Repeat.
Given mean of 52. What about this part of it that says a random sample of 100 gave a mean of 52.6 and a standard deviation of 14.5? What about this mean?
You're breaking up.
I'm asking you, what about this mean? It says
The
random.
52.6.
Yes.
The 52.6, remember that's your sample mean. That's your bar X that you're going to use in the calculation.
Okay.
This is bar X. So that will come in play when you use a test statistic. Let's go back to the formula. Remember the test statistic Z is bar X minus the mean given. See it here? Bar
Yes.
X.
All right. Yes. Okay.
Yeah. Yeah. So don't worry about that given there. That's for when we get to the test statistic. So just like the previous example, we use the 68.5 sample mean. That was our bar X.
Okay.
First one again, they gave us the mean has increased to 51. That was our bar X right there.
Okay.
Yeah. So in this case now, we can say, all right, our null hypothesis is we're proposing that the mean is just 50. So now our alternate hypothesis is that we're proposing that the mean has increased. So mu is greater than 50.
Right.
So now we find our test statistic Z, which is bar X, 52.6, minus the mean of 50 divided by sigma, the standard deviation, which is 14.5, divided by the square root of n, and n is 100. Notice they always give us some easy numbers for n, 100, 49. You know why they do that? They give us numbers that when you square root them, you get an exact number. Square root 100, 10. Square root 49, 7. Square root 36, 6. Notice they don't give no rough sample like 250. When you square root 250, you get 15 point something, a decimal. But if I were setting an exam, I am putting some rough numbers. So your calculation will get weird.
I get 36.28. 36.
So when you put everything in it,
Yeah.
36,
Let me go there.
that's a very big number.
Let me go there. 52.6 minus 50. 14.5. Square root of 100. 1.7. 1.8.
How much you got?
1.8 because I wrote it.
1.8?
Yeah.
Yes, that sounds about right, man. Because anytime you get something bigger than 3, just start check it over. All right? Want to get a value bigger than 3, just start checking it over. Something might be off. So you got 1 point how much?
1.8. I got 1.793.
1.79. Don't round it up yet. Put 1.79. Why? What if the rejection region is 1.795 and you round up to 1.8? Right? You see, we can throw 4 numbers, so we don't want to be rounding up so quickly. So 1.79, we'll work with that. So in that case now, if it was a case now we had 1.7915, then you could round up to 1.792, because then that's trivial. But rounding up from 1.79 to 1.8, big difference. So in this case now, we have that's our rejection region now. So our rejection region, because it's greater than the rejection region is when Z is greater than Z alpha. So at 1% significance level, I want you to look at what's 1% significance level for me. So look at the table and look at 1%.
2.32.
Good. So our Z value is 1.79. I will check in if it's greater than 2.32. Is that true?
No.
No. So in this case, we don't have enough evidence to reject the null hypothesis. So rejection region is not satisfied because that's not true. That's not true. So in that case, we can say we do not have enough evidence because it's not bigger than it. So we do not have enough evidence to reject the null hypothesis. So even though the sample mean for the 100 is 52.6, from the 100, that still don't guarantee overall the mean has increased. The mean can still be 50, it's just that the sample them that you take out, that make the mean be 52.6. But the rest of them, the rest of the sample them, maybe the rest of a mean of 48. 48 and 52, add up the total, probably balance back to the 50, don't?
48 and 52.
Yeah, I'm saying, what if we don't know what's the population size? We're saying that the random sample of 100 gave us a mean of 52.6. I'm saying, what if the total data collection was 200 of them? Maybe the other 100, the random sample from those other 100 maybe would be 48.4. I am saying if the other 100 is 48.4 and this 100 is 52.6, and you check them out back, average the whole 200 now would give you the 50. You get what I'm saying?
Yeah.
I'm saying there's not enough evidence to suggest that we can reject, even though we're getting from this sample, it's bigger than the 50. So there's not enough evidence. Now, when they give you with this, it's very easy. But let me tell you when it gets tricky. It gets tricky when it's proportions. It gets really tricky when it's proportions because proportions is percentages, percentages is decimals, and people don't like working with decimals. That's just the truth. But it's the very same thing with proportions. Null hypothesis, just gonna be P equal to PO, which is the proportion. So maybe you tell me, say, 60% of Jamaica votes for the Labour Party during election time. That's what you tell me, 60%. And I might propose and say, I believe it's greater than that. So that would be my alternate. So your proposal would be P equals 0.6. That's 60% vote for Labour Party. But the alternate now is I am proposing that it's greater than 60% vote for Labour Party. That's the alternate. So proportions is just percentages. Now the test statistic. Now the test statistic is found by the proportion given in the question, your sample proportion, that's why I see a hat on it. This right here, mean hat. So this is the sample proportion minus the proposed proportion divided by the standard deviation of the sample proportion. But remember, standard deviation of sample proportion is equal to the square root of PQ over N. Square root of PQ over N. So you're going to use this formula for your test statistic. Now, the rejection region are the exact same. The rejection region don't change. That's a beautiful thing. Rejection region stays the same. Whether it's one tail or two tail, it stays the same. Make it really nice, right? Cool?
Okay.
All right, so we're gonna do 2 questions and we can jump into the paper from last year. So I don't want to do the first one because the first one don't give us the significance level. I don't want to be making up significance level. All right, so this second one, it says a manufacturer claims, so I'm gonna bring it to the white screen. So a manufacturer claims that a manufacturer claims that a particular brand of seeds has a 90 has a 90. Wait, this is in the way. Let me move it. Why am I seeing? Why is my name here?
It's always there.
Repeat.
It's always there.
No, it is blocking the, I can't see what it's saying. There it is. It was over the percentage. So here it goes now. So it says a manufacturer claims that a particular brand of seed has a 90% germination rate. To test this claim, 150 random selected seeds are planted, and it is noted that one of 124 germinate. Does this provide evidence at 1% significance level that the manufacturer is overstating the germination rate? Let's check it. So the manufacturer, first thing we're going to write down is our null hypothesis. Or null hypothesis is that in belief, say, a particular brand has 90% germination rate. So our P is equal to 0.9. That's P. That's what in believe. Crazy. In believe, say P is 0.9.
This is a when it once you see the percentage side, I know it's a proportion.
Repeat.
I said once you see the percentage sign, I know that is a proportion test.
Yes, once you see percentage, it's proportion.
Right.
Now, H1 now is our alternate hypothesis. Now, alternate hypothesis is that, is there evidence to state that he claims that overstating. Now, key term is overstating here. What does overstating mean?
More than what you expected.
More than. So we're trying to see if, what if I might try to boost this up, right? What if I boost it up? What if it actually less? So our alternate hypothesis now is we're going to test to see if this man overstated. So if P is actually less than 0.9, that's what we're going to be checking out. I want to check if he's lying. What if he's lying? Because you know a lot of brands lie. For example, Big Colgate. Colgate overstate, and if you take up a Colgate box of toothpaste, it tells you say it kills 99.99% of the germs. And I was watching a documentary on YouTube, and it shows it with a lot of statistical evidence showed that it killed about 94%. And they said 99, you know, and people can just run with that. But of course, that's what Colgate do. They have to big up themselves, right?
Mm-hmm.
That's just a part of their marketing strategy. So of course, now we're going to test to see if this manufacturer is lying. So now we need to find our test statistic. Now, first, before we can find our test statistic, we need to find P hat. Now, P hat is going to be equal to, notice them, so to test this claim, 150 randomly selected, and out of that 150, 124 germinate. So P hat, the success was 124 out of 150. Now put this in a calculator and tell me what you get.
Zero 0.8266.
0.826. What a man wicked. 82.6% from his piece is, this is from 115 or this is 82%. But then again, we don't know. Still don't have enough evidence yet. Looking at it, we're probably already assuming that he's lying. But let's not take it for granted. Let's actually look at what the statistics is saying.
So we're going to do the test now.
So our test statistic now, which is our P hat minus P divided by the square root of P times Q over N. So let's actually work it out now. So our P hat right here is 0.826 minus 0.9 divided by the square root of 0.9 times 0.1 divided by N. And N was our sample size Our sample size was,
Is Q 0.1?
sorry, well, Q, I used the wrong one here. Remember what is Q?
But if P is 90%, Q must be 10%.
Yeah, but I just want to go back to, right, here we go, or PO. PO, yeah, we're fine. All right, so P is 0.9 times our Q 0.1 over the sample size 150. Here it is, 150. That's it. We'll put this in our calculator.
Isn't that the square root? You're going to
Yes, square root of it. Yeah, square root of it. Yeah. So we'll put all of it in the calculator.
0.86 minus 0.9.
We bring out the calculator as well.
0.8.
0.826 minus 0.9 divided by the square root of, in bracket, fraction button, 0.9 times 0.1 divided by 150. I want to know what you get first.
9 minus 0.1 square root 1.50. Negative 10.07.
I get negative 3.
I'm gonna do it again.
Yeah, anytime you're getting those 10, you know something is off. It always has to be between 0 to about 3.
06 minus 0.9. Putting the I'm putting okay. 0.9 0.1. Not getting it to go on the bottom.
How much you get?
Still getting the 10 point something. 26 minus 0.9. We'll put in the bracket first. I'll put the fraction button first.
I don't get what you mean. Put in there. Let me bring out the calculator and follow what you're saying. Can you repeat?
When you after you put the 0.826 times the 0.9.
All right, press the fraction button at the start.
No, that's what I did. After
Yeah,
that, then what?
so you put the 0.826 minus 0.9, right? They go down and they press the square root first.
Okay.
After you press the square root, then press the fraction button. You want to type it just like it is. So I'll display it on the screen, just like how this formula is. You want to put it in just like that. So you press the square root, then you put it was here, 0.9 times 0.9 times 0.1 over n, 150. You press equal. You want to type it just like how it is here, your test statistic.
The square root button first, then the fraction sign.
Repeat.
The square
Yeah,
root button first.
square root, then the fraction button again. Yeah.
And then you just go down the bottom.
Yeah, you put in the numerator, then square root.
Negative 3.0.
Negative 3.02, yes. Nice. So that's our test statistic, negative 3.02. Now, because it's a one-tailed test, then our rejection region is when it's less than, we're testing is Z is less than negative Z alpha, right?
Mm.
And we're looking at a 1% significance level. So Z, which is negative 3.02, is less than negative. Look at 1% significance level for me.
Which table is that? Table 4?
Using the table, 1%.
The same table that was using before?
Yeah, the same table that I sent the picture of.
1% is 2.326.
Good, 2.326. So my question to you is negative 3 less than negative 2. Is negative 3 less than negative 2 point something?
No.
Negative 3 is not less than negative 2. Draw a number line. Always draw a number line and picture it. 0, 1, 2, negative 1, negative 2, negative 3. Negative 1 less than 0. Negative 2 less than negative 1. Negative 3 less than negative 2. Isn't that so?
Yeah.
So it's true. I know what's confusing, you know. We're just looking at the positive of the number and say 3, but 3 bigger than 2 point something. No. So if I tell somebody is negative 1 less than 0, you're not going to tell me negative 1 is bigger than 0. No. So you have to look at the sign, important. Right? So anytime you feel confused, draw the number line, all right?
Okay.
Yeah, trust me, the number line, it saves lives. Just draw the number line. You can't make a mistake with the number line. So in this case now we can say, since this is less than it, we're in the rejection region. So yes, we reject the null hypothesis. So since we're able to reject the null hypothesis, let's now go and nice it up, even though it's not a paper tool. What you're saying is that the manufacturer's claim is false. So you're gonna say the manufacturer claim is false. You can even nice it up and say, he is a wicked man for such an exaggeration. Yeah, man, just make your paper nice, man. He's a wicked man for such an exaggeration. Put exclamation mark, make whoever mark a paper would smile. He's a wicked man for such an exaggeration. Exaggerate from all the way at 90. Such a big rejection region. First, his sample is showing us that 82% is 82%, you know, 82% is germinating. Input a whole at 90. No man, come on, better did put 85%. But he put a whole at 90. No man, he's a wicked man for such an exaggeration. That's a wicked. Imagine, for example, I'm a math teacher and maybe my pass in pure mathematics 93 from last year. And imagine I were to tell you that, well, my pass rate is 99%. Isn't that very wicked to state that? That's very wicked, no. Because then, of course, many persons are going to come and say, oh, well, if sir have 100 students, chances are only one will fail. When the truth is that it's a 93% pass rate. So you can see how the 6% is very is very deceitful. It's very deceitful. Can't give numbers like that, so we can say that's a wicked man. Right, but it's just adding humor to the paper. So now we're able now to look at some past papers. This is last year. As I said, the past papers before last year wouldn't have been like this. It's only last year because of COVID that